Hello viewers, welcome to Coding Introduce channel. Hope you are doing great. If you haven't subscribed to the channel yet, please go ahead and subscribe. I have created a bunch of playlists to cover various categories of problems such as BFS, DFS, dynamic programming, and so on. Please check them out. I have uploaded the code for this problem to the GitHub repository. You can get the link from description below this video. Let's jump into today's problem. Even odd tree. A binary tree is named even odd if it meets the following conditions. So we are given with a binary tree and there are some conditions to say whether it is an even odd tree or not, right? So the root of the binary tree is at level index 0. Its children are at level index 1. Their children are at level index 2. So basically in the binary tree the root is at level 0 and root's child are at level 1 and their child are at level 2, right? And the second condition is for every even indexed level, all nodes at the level have odd integer values in strictly increasing order from left to right. So what we are looking for is at an even indexed level. That means at a level 0, level 2, level 4, level 6 and so on, right? At those places we should look for odd integer values. So we should have only odd integer values, and those odd integer values should be strictly increasing from left to right. That's the second condition. And the third condition is for every odd indexed level, that is level 1, level 3, level 5 and so on, right? Those are all odd indexed levels. All nodes at those levels have even integer values in strictly decreasing order, right? So basically even index level should have odd elements and odd index level should have even elements, and both of them should be strictly increasing in the first case, and the second case is strictly decreasing from left to right. So those are three conditions. If they met, then we will say okay, the given tree is even odd tree, otherwise it's not. So that's what we have to determine, right? So let's go ahead and look at one example to understand what actually the values will look like and how we are going to solve this particular problem, right? So example 1, they have a good nice picture for the binary tree. So the root is number 1, right? So that is at level 0. That's what we know, right? That's the first condition, right? So root of the binary tree at level index 0. So that is at level 0. So level 0 happens to be even index, right? So we need to have odd numbers there. So 1 is an odd number. So we are good with that. Then since first level, that means 0th level is done, we'll go further for the next level, right? So 10 and 4 are the children of root node. So and the children of root node will be at the level 1, right? So level 1 is odd index level. So at odd index level, as per the condition 3, we need to have even integers. So 10 is even and 4 is also even. Good. So that's till that point in time the condition is satisfied, and the next condition is strictly decreasing order from left to right. So we have 10 onto the left, and then when we travel from left to right, 10 comes first and then goes to 4, right? So they are strictly in decreasing order. Let's go through the next level, that is level 2. That is again even index level. So we should look for odd elements here, right? So the elements are 3, 7, 9, right? Good. So they're all odd and they should be strictly in increasing order. Yes, from left to right. So 3 is on the leftmost, and then next comes 7 and next comes 9, right? So 3, 7, 9. So they are all in increasing order. So the last level, again, that is level 3. 3 is an odd, right? So odd index level. So now we should have all the elements as even. Yes, we do have all the elements as even: 12, 8, 6 and 2, right? And they are in the strictly decreasing order. So that means this particular tree is satisfying all these conditions, right? So that's the reason why we would say this particular tree is even odd tree, right? So let's go look at another small example where we find the tree happens to be not an even odd tree, so that we have a better understanding, right? So go further. So level 0, that means it's a even index level, so we should have odd, right? So yes, 5 is an odd number, good. And then level 1, we should have even values, that should be decreasing, right? 4 and 2, yes, they are decreasing. The level 2, this is the even index level, and the values that we are expect are odd values, yes. 3, 3, 7, they are all odd values, but for odd values they should be strictly what? Increasing order, right? They should be strictly increasing order. But in this particular example, we have 3 and 3, they are repeated, so that is not a strictly increasing order, right? So they are like greater than or equal to, but they are not greater than strictly. That's the reason why we say, okay, this is a false, right? So this is not a strictly increasing order. Likewise, so if you look at the way that the pictures are laid out and how we are going level by level, right? So we are processing the nodes in the given binary tree by levels. So first we look at level 0, and then we should look at level 1, and then we should look at level 2, and so on, right? So that means we are going a level order traversal, right? So there is another name for that, breadth first traversal. So that means at each level all the nodes would be traversed before moving on to the next level, right? So breadth first traversal. So we are going to use breadth first traversal in order to solve this particular problem, right? So as we know, breadth first traversal is we consider one level at a time and then validate all these 3 conditions, right? So in actuality, even though there are 3 conditions, right, the first one is just to give you what level is what. Basically root is at level 0, that's all what it says, the condition 1. So basically condition 2, the even index level and the odd index level. So these are the conditions that we are going to validate while we go through the entire tree, right? So in order to do that, right, so basically what we are going to essentially say is, so we will go through each level. So as noted, so the level will be initialized to 0, right? Level will be initialized to 0. So at level 0, obviously there is only one node, that is called root node, right? So we would just check as long as the root node is there and its value is what? Level 0, right? Level 0 means we are expecting odd values. So root should be odd. As long as that satisfies, we can move further, right? So that's what the condition, right? So otherwise we can say, okay, it's not an even odd tree, because that's what we have to return, right? If it is even odd tree, we have to return true. Otherwise we have to return false, right? So now what we are going to essentially do is initially check for that. And even before that, there is a base condition. What is that? If the given tree itself is null, right? If there is a null tree, that means there are no nodes in the tree. Then we would obviously say, okay, it's a even odd tree, right? So that's what we are going to do. So to start with, we will say if root is null, return true. So I have shifted my focus to the code so that while we walk through the code, we try to understand how we are going to really process this through the breadth first traversal. So since we are going to process all the nodes in a given level, right? So we are going to use the queue data structure here. Okay, so we have declared a queue which is holding the values of tree node, and initially we are given with root, so we are going to add root node into the queue, right? So we added the root node into the queue and initialize the level to 0, and So we are going to go through this queue as long as queue has some nodes in it, right? So since we just added a node, right, enqueued, the count in the queue should be obviously greater than 0. And now, so since we have to go through each level by level, right? So at a given time, what we are going to ensure is a queue has only the nodes which are pertaining to a single level, right? So we will read only those many number of nodes per level, right? So now, while q.count is greater than 0, we get the count, the number of nodes currently that are there in the queue, right, at that particular time. So that is the count. So for when we inserted only the root node, the count would be 1, obviously, right. And we are going to use an extra space here. What is this will be used for? We are going to put all these values, right, on each level. We are going to put all these values on each level in this list, right? And then we validate these two conditions, the condition 2 and condition 3, right? So we go through that many nodes and push all the values into this list, basically, right? Extract the values, extract the node from the queue and put the value into the list. So once we have that, and the next thing that we are going to do is, obviously once this level is done, we will have to process the next level, right? So in order to process the next level, we need to add the current level's child nodes to the next level, right? So for that, what we are going to do is current nodes left, if it is not equal to null, we add it to the queue. If current level right is not equal to null, we add it to the queue, right? So this is how we are able to put the nodes for the next level. So once we have processed the count number, so for level 1 it will be just one node because only root node. For level 2 it will be 2 nodes for this example 1, right? 2 nodes like that. So once we have processed that many or count many number of nodes, we come out of this for loop and see whether the values are satisfying these conditions, right? So if level percentile 2 is equal to 0, that means even level, right? Otherwise it's odd level, right? Simply. So if it is even level, we'll have to make sure the elements are odd. So if it is an odd even number, we just say return false then and there, and then go through the entire collection of elements in the cur level. So if at all the element is even or the current element is less than the previous element, so it should be strictly increasing order, right? So that means current level should be greater than previous element. If so, we are good, otherwise we are going to return false, right? So that's what it is. So this is for the even level. So odd level, it is just little bit of change. As long as it is a odd number, we return false, or if it is odd number or the current element is greater than or equal to the previous element, we just return false, right? So that's the code that we are going to go through in order to validate the condition 2 and 3. So this is even index level. So the condition is conditions number 2, right? And odd level conditions number 3, right? So odd level is this one, that's what I'm calling conditions number 3, and this one condition number 2, that's what I'm calling, right? So at the end of it, after processing the levels, if it happens to be following the condition 2 or 3 at respective level, we are going to increment the level, right? So this process will be continued until the queue has 0 elements or any of them return false. But once you exhaust the queue, right, that means all the levels in that binary tree are satisfying these two conditions, right? So at that particular time, you exit the while and then return true, right? So that's how we are able to proceed. So now let's look at the time and space complexity for this, right? Time and space complexity for this. So how much time we really need here, right? So let's say there are n nodes, right? N nodes in binary tree, let's say. So that means we are going through the n nodes through this while loop one time, right? It's in a best case. For example, this true case, we are going through all the nodes, right? That's what we need to check. All the nodes we are looking at. But of course, if at level 1, if any of the conditions fail, right, we just return. But we are going to consider the positive case where we are going through all the nodes in the binary tree. So that's why I'm calling n nodes. So the time complexity would be how much? It's order of n. So is that it? Is that it really? Right? So is that it? We are going through this, that's correct, but there is more processing that we are actually doing for even level and for odd level, right? So we are going through the elements one more time, right? For every level we are going through them one more time. So that means each element or each node being visited twice, right? So in the while loop, while as part of the queue we visit once we put it to the curl level, we are visiting them again depending on the level, either in if or else block, right? So that means each node is getting visits 2 times. So that means we will say the time complexity is order of 2n, right? But since we are going to drop all the constants from big O notation, it will be still order of n, right? That's the time complexity for this particular algorithm. And go to space complexity. So how much space we are essentially using here? So one space we are using it for q, right? That's one. And then another space that we are using it for is the curl level, the list, right? So that means at curl level, how many number of elements it could store at a given point in time? Obviously 2 power L. So if L is level, then 2 power L number of elements in curl level list, right? Curl level list. And of course the queue also will have the similar number of elements, right? So queue also will have 2 power L number of elements in a given point of time, right? So in that particular case, what we are going to say is, since we don't know what is the maximum level for a given binary tree, right? But if you have n nodes and the tree is well populated, that means it's not a left skewed tree or a right skewed tree, then in that particular case n by 2 nodes will be in the last level, right? N by 2 nodes will be the last level. That means the queue will have the time complexity of order of n by 2 plus the space that we are using for current level, that will be again order of n by 2. So that means it will be order of n. So this particular algorithm is the time complexity of order of n, and space complexity is also order of n, right? So there is one improvement that we could make here. So instead of using an extra space for this curl level, we can get away with a simple variable. Although it is not going to really change the big O notation complexity, but in practicality it would use lesser space, right? So for example, if the queue is using, let's say if n is equal to 100, If the queue is using 50 spaces and the list is using 50 spaces, then 50 plus 50 is 100, right? But if you eliminate the space complexity required for the curl level, right, it will be using only 50, that is half of the space. So big O notation, it will be still called as order of n, but in the practical usage, it will be half of whatever it will be used with this. So let's go look at the improved code now, right? So let me show that improved code. So here in this particular case, what we are essentially saying is, so here I have commented this code out saying curl level, we are not going to use this curl level anymore, but instead of that we have assigned a previous integer, that's it, just one integer. So based on the previous, we are going to validate these two conditions. So what we are going to do is, as we go through the elements in the particular level, we are going to validate it. If the level is even level, we just put whether the element is odd. If it is odd, we are good, but if the element is even, we are going to return false. And then if previous is not assigned, so why did I assign previous to 0? In the problem it stated that, let's go, there are constraints. The node values are ranging from 1 to 10 to the power of 6, right, 10 to the 6, right, it's a million. So the node value will be between 1 and a million. That's why I assigned the previous pointer to 0, right? Good. So previous is assigned to 0. As long as previous is assigned to 0, that means that is the first node that we are visiting in that particular level. So once we assign the previous pointer, we always make sure it's less than the n dot value in the case of even level, and it is greater than the previous in case of odd level, right? Like we talked, this is even level and this is odd level, right? So the code is pretty much similar, but except that we are not using the extra space, the list of extra space in this particular case, right? So there is a little bit verbose code that I wrote here in order to make the things easier to understand, right? So basically we are checking the previous value is greater than or equal to n dot value. If so, we just return false, and then we are going to update the previous pointer, right? So once we go through the current level, right, we are going to increment the level, and once we exhaust the queue, we will return true, assuming nowhere we were returning false. That means all the elements in the particular given tree are valid with the given conditions, right? So in this particular case, the time complexity and space complexity would be remaining same. The time complexity is the order of n and space complexity will be order of n by 2. Since we are going to remove the constants anyway, it will be still order of n. As we said, the big O notation complexity, there is no big change, right, because we are using the queue, right? But in reality, this code would use half the space as the other code, right? But big O notation, there is no particular change. We still call for both these codes order of n time complexity and order of n space complexity. If you have any further questions, please post them in the comment section below. I will get back to you as soon as I can. I have posted this code to the GitHub repository. You can find the link in the description below this video. If you haven't subscribed to the channel, please go ahead and subscribe and also share among your friends. Please click on the bell icon so that you will be notified about all my future videos. Thank you for watching. I will be back with another problem very soon. Till then, stay safe and goodbye.